G'day everybody, this is our second lesson with the normal distribution. In this lesson we're going to talk about confidence intervals. Because the normal distribution is symmetrical, we'll talk about how we take advantage of this symmetry to express different probabilities associated with a normally distributed variable. And with our CAS calculator we're going to talk about the inverse normal function and what type of problems would we use that for. Before we go into anything, let's review what we've covered in our previous lesson. I'm choosing a different example here. Let's use this scenario. So the time people take to walk a certain bush track is normally distributed with a mean time of 45 minutes and a standard deviation of 7 minutes. We're going to look at three questions here. We're going to talk about what is the variance of this distribution, what proportion of people will take less than 30 minutes to complete the walk, and what's the probability that X lies between one standard deviation above or below the mean of this distribution. The first question is an easy one. The standard deviation is 7 minutes. The variance is simply the square of that, so our variance is 49 for this distribution. Let's have a look at the second question. What proportion of people will take less than 30 minutes? Here we're looking at a sketch of the distribution. You can see I've got my mean in the middle, and I've used the standard deviation. 3 standard deviations above the mean is 66. 3 standard deviations below the mean is 24 minutes. Practically everybody finishes this bush track in between 24 and 66 minutes. So in the second question, what's the proportion of people that will take less than 30? I've shaded that part of the function, and we're looking for that area. We're going to use our normal CDF function on the CAS calculator, and so the answer, the probability that X is less than 30 minutes is 0.016, or 1.6% of people will take less than 30 minutes. Our next question concerns the probability that the amount of time will fall somewhere in between 1 standard deviation above, 1 standard deviation below the mean. With a standard deviation of 7, that means the time we're interested in is the times between 38 and 52 minutes. I've shaded the diagram on a sketch. Again, we're going to use our normal CDF function with a lower bound of 38 and an upper bound of 52. And that turns out to be 0.683, or 68.3% of people will take greater than 38 minutes, less than 52 minutes. This result is the same as it's going to be for any normal distribution where we're interested in the area 1 standard deviation either side of the mean. So this is what we call our typical confidence intervals for a normal distribution. So for any normally distributed variable, the area that lies under the curve within 1 standard deviation either side of the mean is 0.68 approximately to 2 decimal places, 68%. Once we go out to 2 standard deviations either side of the mean, that area jumps up to 95%. You can see that in the way that it's shaded. And then by the time you look at 3 standard deviations either side of the mean, we're talking about 0.997 or 99.7% of the outcomes will be between those two boundaries. And that's why I say practically all outcomes will lie within 3 standard deviations of the mean for a normally distributed variable. We're going to have a little chat now about symmetry. We're going to use a certain brand of eggs. that have a mean weight of 55 grams and a standard deviation of 2.4 grams. And you can see I've defined the distribution using those quantities. I don't mind putting 2.4 squared for the variance, because as I've said before, we never use the variance in a problem, we always talk about the standard deviation. So, using our confidence interval, our one standard deviation below, above the mean, so within the limits of 52.6 grams, 57.4 grams for an egg, 68% of eggs of this brand will lie between those two boundaries. Now, because we're looking at an area that's situated both sides of the mean, exactly one standard deviation, that means that if 68% of our area is between the boundaries and it's a probability density function with an area that has 1, that means that 32% lies outside of those two boundaries. And splitting that in half, we've got 16% of the eggs have a weight but lower than 52.6 grams, and 16% of the eggs will have a weight that's greater than 57.4 grams. So we know that just from the symmetry of the distribution. We don't have to do any more calculations for those two facts. So there you can see I've shaded in the area that's above one standard deviation, and because of the symmetry we're able to say to 2 decimal places that probability is 0.16. Because of that, we could also use the complement. What is the area lower than one standard deviation above the mean? So from negative infinity up to 57.4, without needing our calculator again, we can look at 1 minus 0.16, or we can take the 0.16 on this side and the 0.68 and add those together. Either way, the probability that the weight is below 57.4 grams has to be 0.84 to 2 decimal places. And here's one other example of using the symmetry. So the probability that x lies between the mean and one standard deviation above the mean, as shown by the way I've sketched this area, 68% lies in the middle. So the area that has been shaded there within those two boundaries must be 34%, or 0.34. So for all normally distributed variables, there's a lot of facts that we can work out just from the symmetry of that distribution. For the last part of this lesson, we're going to look at a new problem. We're still sticking with the scenario of people walking along a certain bush track. In this case, we're going to consider the best 23% of walkers, or the bottom 23% of times taken. Let's say that we recommend that those people also take a mountain hike, as they'll be the fitter people that are ready to take on that challenge. What time are we going to use to decide whether I am going to be in that best 23%? Once again, I've sketched that situation, something I always encourage you to do. So here I've got the bottom 23% of the area from negative infinity up to this point, and it's this value that we're trying to solve. So that area shaded is 0.23. It's a distribution that has a mean of 45 and a variance of 49. How do we find out this particular value here? What time is going to give us that cutoff for the lower 0.23%? To put it mathematically, we're solving A, where A is here on the horizontal axis. We're solving A such that the probability that x is less than A is equal to 0.23. And here we use a new function in our calculator. We find it in the same place under the distributions in the probability menu. The third option is called the inverse normal. When we select that function, we get a pop-up that asks us for 3 inputs. It wants the area, which is 0.23, and the mean and the standard deviation for that distribution. Once we click OK, it's going to give me this value on the horizontal axis for that distribution. And it turns out for this particular problem, that value is 39.8 minutes. So on this bush track, if I was to take less than 39.8 minutes, because it's a normally distributed variable, that gives me the confidence that I would be in the best 23% of walkers on that track. Really important point when using the inverse normal function. This input of area is always the area from negative infinity up to a certain point. So it's never the area that's in between a lower and an upper boundary. That lower boundary is not finite, it's always negative infinity. And that's really important to understand when using this function. So the only time we can use the inverse normal function to get a value of x is when we know, or when we've worked out, the area from negative infinity up to that point. So that completes the second part of this topic of the normal distribution. We've got one more part to go. In this lesson we've talked about the confidence intervals, 1 standard deviation, 2 standard deviations, 3 standard deviations above or below the mean. We've talked about the symmetry of the normal distribution. How do we take advantage of that symmetry to find out other facts or probabilities associated with a variable. And at the second part of this lesson we talked about the inverse normal function, how we use an area that's known on a graph to give us the value of a variable that's associated with that area. Please write down any questions you have and complete the Google form that goes with this lesson to log your attendance and to check your understanding. Thanks very much.